Okay, so let's get started with the actual lecture. There's condition generation. So language models, which we've talked about a lot before, are generative models of text. So basically, they give you a probability distribution x over x, and you can sample a sentence from it. So if you train it on a bunch of Harry Potter books, you can get something that looks a little bit like this. Like the Malfoys said Hermione, Harry was watching him. He looked like Madame Maxime. When she strode up the wrong staircase to visit himself, I'm afraid I've definitely been suspended from power, no chance indeed, etc., etc. This actually is a little bit old. This is from a couple of years ago, and language models have made incredible progress in the past couple of years. And actually, they can generate things that are significantly more coherent than this. They still do make these mistakes. I think maybe some people have seen Google just made a big post about a new dialogue model that they published. And it's interestingly pretty coherent, but if you look at the actual outputs, there's lots and lots of things like this as well, logical inconsistencies and stuff like this. So, we've come a long way, but we're, still not completely there yet. On the other hand, conditioned language models, I'm intentionally calling them conditioned language models here. And what I mean by a conditioned language model is it generates text according to some input specification. So it's a distribution over language, but conditioned on something else. And the input can be anything, and the output is text. So we have the input could be structured data, and the text could be a natural language description of that structured data. The input could be English, and the output could be Japanese. The input could be a document, output short description, utterance, response, image, text, speech, transcript. And these correspond to tasks. So if you ask an old school NLP person what natural language generation is, they will mostly be talking about the first thing here. And this is actually one of the widest use cases of natural language generation. And so structured data could be anything from weather reports to basketball scores to the US Census, et cetera. So if you look at Wikipedia, many of the articles are automatically generated about like towns or something like that are automatically generated from US Census data. So this is actually pretty widely used. There are whole companies that are devoted to doing this kind of thing. What are the other tasks on this thing here? Should be an easier than your quiz questions. Any ideas? Or what's the first one? Sorry, that I haven't covered yet. Yeah, machine translation. Next one. Summarization.
Dialogue.
Yeah, I'd say dialogue or dialogue response generation, maybe. Yeah. Image captioning and
transcription. Speech to text.
Yeah, speech to text, speech recognition. Yeah. So as you can see, like the types of tasks that you can formulate in this general framework are extremely broad, and each of these are a little bit different. So for each of them, considering how each of them are a little bit different, you can do even better. But like one of the big kind of revolutions in neural networks for NLP is basically that you can now do at least a decent job at solving all of these with a single model and understand all of them. Okay, so formulation and modeling. So when we calculate the probability of the sentence, like we've done before, we basically step through the sentence one by one and predict the next word given the context. But conditional language models predict the next word with the addition of some sort of other added context in addition to the sentence itself. And one type of language model that we've talked about are the language model, like an RNN-based language model, maybe an LSTM-based language model, where you step through the sentence one at a time. And you can think of another type of a conditioned language model, where you basically have an encoder that encodes whatever context you want, and a decoder, where the decoder generates the output one at a time. And this is extremely simple. It's an extremely simple concept that nonetheless can be quite useful for particular varieties of things. So this isn't like super widely used in things like machine translation nowadays, but something like dialogue response generation or image captioning or things like that, you can use a model that looks very similar to this, where you just swap out the encoder and take whatever single vector you get from the encoder and use that to initialize the decoder. So when I say initialize the decoder, basically what you're doing is you're taking some sort of hidden state that you get from the encoder, and there's a number of ways you can use this. One way is to initialize the decoder with the encoder's hidden state. So if you're using something like an RNN, you just take the hidden state of the RNN that you get out last from the encoder, and you replace the initial hidden state of the decoder with that. Another thing you can do is do a transform. So like, let's say you wanted to use a bidirectional RNN of 512 units in each direction, but then you wanted to use a unidirectional RNN in the decoder side to generate the output. The problem would be this vector would be 1024, size 1024. This vector would be 512. Or maybe even if they're the same size, maybe they're in a slightly different space because, Japanese is in a different space than English, or documents are in a different space than summaries. So you can do some sort of transform, which also allows you to change the size of the vector and then initialize the decoder with that. And another thing that people used to do, maybe not do quite as much anymore, is just input it at every time step. So you have the encoder, you take a vector, and you input it at every time step into the decoder. But either way, basically, this involves taking an encoder, getting a single vector from it, and feeding it into the decoder in some sort of fashion. So this is actually, like, conceptually, this is extremely simple. Historically, in 2014, there was a paper that I assume that many people know called Sequence Learning with Neural Networks. And it did exactly this. It basically initialized the hidden state of the decoder with the hidden state of the encoder and demonstrated you could do surprisingly well for neural machine translation. And this was the moment that I decided I really needed to learn about neural networks, actually, when I saw this paper. It was like, wow, that's pretty impressive. But realistically now, for a lot of language tasks, we'll be using attention, which we'll be talking about next time. That being said, there are a lot of things that are shared between this simple model that you could basically do with all the knowledge you have so far, and other methods like methods that use attention. And one important thing is that now, instead of just randomly sampling things or randomly sampling from the probability distribution, we need to think carefully about how we generate outputs. And the generation problem is we have a model of P of y given x. And given this, how do we use this to generate a sentence? And this was covered a little bit in the reading, but I think this is really important to think about carefully. And I'm going to talk about it a bit. Some of this I might just talk about on the whiteboard and just not on the slides, but I think it's really, really important to think about carefully. And so there's two methods. One method is sampling, and you try to generate a random sentence according to the probability distribution. Another thing is argmax. So you try to generate the sentence with the highest probability. And these two can be used for different things. Like one thing I mentioned in the reading is that you might want to use sampling when you actually want different responses or diverse responses. You might want to use argmax when you want to try to generate the sentence, generate something like the best possible output that you could get for a certain input. Another way to think of it is basically sampling. What it does is it tells you what the model thinks. It gives you an idea of the probability distribution that the model has learned. So if you sample things according to the probability distribution, you sample 100 things. These tell you essentially what does the model think are plausible outputs for this particular input? On the other hand, the argmax tells you what does the model think is the best, most likely possible output for the input. So the good news about ancestral sampling, or about sampling, is it's extremely simple to do well. You can just, in order to do this, you just write this variety of code, which is like while yj minus 1 is not equal to the end of sentence symbol, you sample the next word from the output. And importantly, this is an exact method to sample directly from the probability distribution. So if you sampled an infinite number of sentences according to this probability, the probability of getting any individual sentence, or the proportion of any individual sentence in that infinite sample would be equivalent to the probability of that sentence according to the model. So the reason why I'm pointing this out is this is in contrast to any sort of search algorithm where there's no efficient search algorithm to do search over an arbitrary model to find the highest scoring output. And so basically, one thing that we can do is greedy search. So one by one, we pick the single highest probability word, where we step through one by one and pick the next highest scoring word. But this will fail sometimes. And my favorite example of this is, let's say we say, where do you think we are now? Or something like that. And you condition on some information about where we were last week or something like that. And let's say last week you were in Pittsburgh, but you had told somebody that you're flying around a lot nowadays, so you might be anywhere on the East Coast. So then based on this, the model guesses Pittsburgh. With 0.4% probability. New York with 0.35% probability, and New Jersey with 0.25% probability. So what does greedy search here do? No, it picks new because the sum of new of the word new is 0.6. So it picks the word new, and then it's stuck. So it says, okay, I have to pick York next because I think York is more likely than Jersey. So what actually ends up happening in models where you do greedy search, it ends up doing these kind of silly things where it falls into a local optimum and then cannot escape from them here. So what you actually would want to do is, if Pittsburgh is legitimately the highest scoring, response, you would want it to do that. And one way you can fix that is by doing a beam search. And what beam search basically does is it expands the number of possibilities that you keep around before switching to the next one. So if your beam size was 2, then you would have 2 options. One would be Pittsburgh, one would be new. And then you step to the next one, and you see that Pittsburgh ends the sentence with very high probability. And then you have to choose between York and Jersey, and you see that York and Jersey both, when multiplied with the probability of new, have a lower score than Pittsburgh. So you can just reply with Pittsburgh. So this is the reason why beam search works. It prevents you from falling into these kind of things that look good locally, but actually are bad choices globally. Yes?
I didn't understand why now Pittsburgh would win.
Okay, so maybe I can write it up here. So let's say we have probability on the first word. The probability of word number 1 being equal to Pittsburgh is equal to 0.4. The probability of new is equal to 0.6. Then on this, so we keep both of these around, and our highest scoring hypothesis is 0.6. our second highest scoring hypothesis is 0.4. Now we expand these, and let's say everything other than end of sentence just had a negligible probability. So end of sentence has a probability of, end of sentence given Pittsburgh has a probability of approximately 1.
Okay.
And then given new, what's 0.35 divided by 6? Or by 0.6? It's like 0.
Around half point. 0.3 by 0.6, right?
0.35 divided by
0.6 and 0.4 approximately.
0.6 and 0.4. Okay, so let's say it's 0.6, 6 and 0.4. Yeah, that's a very good approximation. So probability of York given new becomes 0.6, and probability of Jersey given new becomes 0.4. But then we multiply these together. So we get 0.6 times 0.6, which is equal to 0.36. And 0.36 is now lower than Pittsburgh, of the whole sentence, Pittsburgh end of sentence. So now we can just throw this out and say Pittsburgh end of sentence is going to be the highest score that we can see. So.
But this whole explanation is dependent on the fact that that probability is very high, end of sentence.
Yeah, that's true. And if that wasn't high, then Pittsburgh might not be the ideal candidate according to the model, right?
Is that correct to assume?
Is it correct to assume? So this is a good question. So there's two questions here. One question is our search algorithm finding a high score according to the model? And is the model correct? Or does the model give us a high probability for a good answer? And these are two different varieties of errors. If our model thinks a bad answer is correct, which happens a lot of the time because our model is imperfect, we call that a model error. And if our model thinks something gives high probability to something, but our search algorithm cannot find it, that's called a search error. So I assumed here that basically our model was correct in selecting Pittsburgh. And it gave a probability of 0.4, and then it gave a negligible probability to something else. But if our model, did not do that, then maybe our search algorithm would find another like non-optimal outcome. So, yeah. Any other questions? Yeah. So there's a bias. There's a bias towards shorter sentences in maximum likelihood trained models. And the reason why there's a bias towards shorter sentences, there tends to be a bias towards shorter sentences in maximum likelihood trained models, is because at every time point, you're multiplying in a probability, and that probability is 1 or below. And that's a major issue in any sort of language generation model. Usually that's an issue because of model errors. So your model is basically assigning a higher probability to overly short sentences. But greedy search causes search errors, and those search errors tend to be in the direction of favoring longer sentences. So basically, greedy search finds long sentences that have a worse model score because it's failing at the search problem, which as a result results in you finding longer sentences. So, so as a result of this, there's actually, like, I can show you a paper. Oops. So let me try to find the paper real quick. And it's this paper here. And it describes this. It describes this in this graph here, where this dark green line is basically they increase the beam size. And as they increase the beam size, the blue score, which is this kind of metric for how good translations you're generating, goes up for a little bit because you start reducing search. You reduce the number of search errors, and you find you don't make silly mistakes like this. But eventually, at some point, it starts going down again, and this is largely this can largely be attributed to the length, to beam search more efficiently finding really short sentences that the model likes. This light green line here is when they divide the length they divide the log probability of the output by the length of the sentence, which I think we also discussed a bit in the reading. So log probability of the output by the length of the output. So instead of searching for the thing that the model actually likes the best, actually thinks is the highest probability, you are searching for the thing that the model thinks has the highest probability on average per word. This has no real probabilistic interpretation. It's just a heuristic that seems to work pretty well, but that's, if you do that, you can see that it largely alleviates this problem, but you're still having some issues at the end where you start doing beam search. And there was another paper, I don't know if I can find this paper immediately, but there was another paper that showed that actually the empty string has the highest probability a fairly large portion of the time in trained machine translation models. So this is a major issue. I'm going to talk a little bit more about this later, but there's a couple ways that we can fix problems like this. One way is by training the model to actually output good sentences as opposed to just maximizing the likelihood. So this problem can largely be attributed to maximum likelihood training, like the standard training that we do. Another thing that we can do is we can do a different way of generating sentences, which is not finding the maximum probability sentence, but rather finding the sentence that we think will likely have the highest score. And this is called minimum Bayes risk decoding. And maybe I'll be able to talk about this at the end of the class, but it's a little bit involved, so maybe I won't talk about it immediately now. These are good questions, though. Are there any other questions? Yes?
I have one. So imagine when we're doing, let's say, something like tagging, pause tagging or anything that is done by a certain DP-based algorithm, dynamic programming-based algorithm. Why can't we use some similar dynamic-based programming algorithm out here? Is it because it fails the Markov assumption that's not conditioned on the previous word?
So the question was, when we do something like tagging, what we normally do in tagging is we either predict each tag independently, or we have some model like a CRF, a conditional random field, which we'll also be talking about later, that basically makes an assumption that only neighboring words interact with each other. So it basically says if we have a determiner to the left, we're more likely to have a noun to the right, but I'm not going to say anything about 2 words ago, for example. Why can't we do a similar thing like we do there and use a dynamic programming algorithm or something like that to generate the output? Is it because that sequence generation fails the Markov assumption? So it basically fails it requires information that's more than 1 word ago. The answer is yes. Basically, it fails the Markov assumption, and any of our strong models for sequence generation or language modeling will not make such a Markov assumption. So the answer is yes, that's the reason. I saw a hand in the back. Yeah. What's a typically good beam size? Let me reference this paper. And the answer is 4 if you're not doing length normalization for Czech English, 8 if you're not doing length normalization for Czech English, maybe 12 or 20 for English German, 4 for German English. And then if you're doing length normalization, maybe really large, but then sometimes that doesn't work. So I don't know. This is just for machine translation. If you're doing some other task, it's going to be different. That being said, 5 has a reasonably good trade-off between accuracy and not being as bad as 1. So you'll notice like 4 or 8 here seems to be okay. You might do better with a little bit other ones, but you could start with 5 and then work from there if you want to adjust that. Yeah.
Are there any other even better techniques for normalization than this? Like before the end of that, like pretty much through line, is that
Yeah.
due to the model there, or is it
So are there better techniques for normalization? And the answer is basically yes, there are. So one other thing that you can do, so I talked about 2 ways to fix this problem. One way to fix this problem is through better training algorithms. Another way to fix this problem is through better search algorithms. A final way that I didn't mention is, or better search criteria, let me say, not better search algorithms, but better search criteria. The third way is through better heuristics for length normalization, and there are some. One example of one is to take the length of your input either take the length of the input or the input sentence itself and use this to predict the length of the output. So either the length of the input sentence or the input sentence itself and predict the length of the output, and somehow like interpolate this this log probability with the log probability of the actual sentence itself. This is also a heuristic, but it's slightly less heuristic, right? It's a learning-based method to say when I see inputs of this particular length, they're generally inputs of this length. So that's another very good question. If this is interesting, remind me on Piazza, and I can post some links to something like that. Yeah.
So going back to the previous question on why can't we use forward backward algorithm or stuff like that. So the complexity of those algorithms is also order of v squared, which is squared in the number of words basically, and that could not be feasible if we are talking about say any.
So the comment, I guess, was, I don't know if it was a question or a comment, but the comment was another reason why you couldn't use like the forward-backward algorithm or something like this is because the complexity is the size of it's quadratic in the size of the label space that you're predicting, and if your vocabulary is very large, that could become infeasible, and that's also true. Yeah. These are all very good questions and comments. If there are other ones, I can field them, but otherwise I can move on. Okay, great. So, yeah, and we have some code examples if you'd like to take a look at them. Another thing I'm going to talk about, which was talked about briefly in the reading, but I'm going to talk about it more here, is model ensembling. And ensembling is combining the predictions from multiple models. So basically, you train multiple models independently. And then you take their predictions and combine them together in some way. And the reason why is because multiple models make uncorrelated errors. So one model might really like think dogs tend to meow, but that is kind of an outlier, and then your other model would think dogs bark. So as long as these errors are in the minority, or when your model is about to make an error, it's very uncertain about the error. So like your model that knows that dogs bark is very certain about the word bark, but your model that thinks dogs might meow is not very certain about meow. The ensemble will tend to favor the model that's more certain. Yes, so that's it. This smooths over idiosyncrasies of the model. So the thing I covered in the reading is linear interpolation. So linear interpolation, this is a slightly more complicated version of what I covered in the reading, but basically it takes the weighted average of m model probabilities. So you have the probability according to each model, and you take the weighted average of them. This is the more general form, where basically you select how much you trust a particular model based on the context, which is something that you can do. But the second term is often set to the uniform distribution. So you just you just say, I'm going to trust every model equally here. One time I actually tried to learn this probability for machine translation models, and my learning model just learned the uniform distribution, so I, I kind of gave up on doing this after that, but that's not to say that will happen every time. It just happened for me in that one particular time. Another method that you can use is log linear interpolation. So log linear interpolation basically takes a weighted combination of the log probabilities and then renormalizes. So here, this is the log probability, and this is some sort of score over the log probability. Usually this will be positive. It doesn't necessarily have to be positive. It could be negative if you have a model that's actively hurting you, for example. So it's a model that tends to be wrong more than it tends to be right. Usually this is positive because you assume that each model is contributing a little bit to the ensemble. Importantly here, you have to renormalize, and the reason why you have to renormalize is the sum of probabilities according to weighted by a probability distribution is a well-formed probability. But the sum of log probabilities weighted by some coefficient is not necessarily a well-formed log probability. So you need to renormalize using a softmax if you want to do this to get a real probability. And this is really important. Actually, if you try to do ensembling without this renormalization, this can hurt you really, really bad. Okay. So if you have two options, the question becomes which one should you be using? Oh, so another thing I should mention about ensembling is this is one of the few things that works almost all the time in neural networks. So in neural networks, unfortunately, there are lots of things that don't work in some cases, but not others. This is one of the few things that works pretty consistently almost all the time. So you train multiple models independently, it will almost always, and use both of them to make a decision, it will almost always improve your results. So it has the disadvantage of having to train multiple models and use multiple models at inference time, so it's slow. But if you really want the last 0.5% of the accuracy, this is a good way to do that. So then the question becomes, which one should you use, linear or log linear? You can think of this in logic in a way. So linear is kind of like a logical OR. And basically what this means, it's like a soft logical OR. And what this means is the interpolated model likes any choice that any model gives a high probability. So like let's say, to give an example, we have the probability according to model 1 is equal to 0.2, 0.1, 0. Actually, maybe this is not right. 0.3, 0.7, and 0.3, 0.7, 0.1. So a linearly interpolated model, if you just calculate these, the average of these two would be 0.3 and 0.4. Wait.
0.6.
Oh yeah, sorry. Yeah, 0.6. This is why we let the computers do the math and not the humans, especially when standing in front of 90 people for maximal embarrassment. So then we have 0.35 and 0.35. So you can see that the first choice, both of the models liked kind of equally. The second choice, the second model liked it. The third choice, the first model liked it. And you can see the choices that one of the two models likes gets a high value according to this linear interpolation. However, if you did log linear interpolation, if anyone wants to pull out like NumPy and actually calculate this, I can't do calculation in regular space, so I obviously can't do calculation in log space. But if you the log linear is more like a logical AND. So the log linear interpolation will favor things that all of the models kind of agree that they like. So I'm pretty certain that in this particular example, if you did log linear interpolation, this first example would have a higher probability. First choice would have a higher probability than the other ones. So this means that you should use them in different use cases. So for linear interpolation, you'll want to use this when you have models that are, you often want to use this for models that capture different traits. You especially want to use this when you have a model that might assign 0 probability to some outputs that another model will not assign 0 probability to. Because log of 0 is negative infinity, which means you would never choose that choice. So to give an example, let's say you have a word-based model that's quite good, but can't handle unknown words, and a character-based model that is not quite as good as your word-based model, but it can handle unknown words. In that case, the word-based model would give 0 probability to unknown words. But if you did linear interpolation, you could still handle unknown words with the character-based model. That would not be the case for a log linear model. So this is important to kind of understand the distinction between these two. Any questions about this? Yes.
When you view the ensembling approach, like when you talk about the different models, is there any inclusion in terms of, I mean, there's a very variant in terms of the architecture or the paradigm that you training or use? What do we use? What's like the minimal
So this is a really good question. So we're talking about different models. How different do they have to be? And the answer, at least with respect to neural networks, is not very much at all. You can even just change the random seed and train different models with different random seeds so they get the data in a different order or they start with different initialization. And you can still do very well with ensembling. That being said, they rely on errors being decorrelated. So if you have two models that have about the same accuracy, the more decorrelated the errors are, the better. So if you can train two models that are very different and tend to make different types of errors, you will see bigger gains in ensembling. But like even just changing the random seed with this is surprisingly effective. Yeah.
Like when we're using log linear, probably have to use softmax, which end of the day might encounter larger, like in terms of latency time. Why not just do something like harmonic mean? Because ideally, even though it would require renormalization, but that should be easier to do. It would probably require a softmax plus harmonic mean end of the day would achieve the same result. That two almost equal values will give it a higher.
Why don't we use the harmonic mean?
And such a mathematically more maybe clear to do with it.
That's an interesting question. Well, number one, it still wouldn't be a probability if you took the harmonic mean. Yeah.
Normalization might be easy because I can't obviously
Yeah.
Intuitively I feel like the normalization might be easier.
That's a good question. I mean, like, I can't think of any theoretical response to this other than yes, like intuitively I feel like the harmonic mean might be better than the arithmetic mean, but that's an interesting question. Yeah. I don't know the answer to that though.
In the log linear model, the interpolation coefficient, are they regular probabilities as well, or is it also log probabilities?
That's a good question. So the in the log linear model, the interpolation coefficients, are they probabilities? And the answer is they don't have to be probabilities. They can be any value you want. And the reason why is because you're renormalizing anyway, so you can do anything you want. For this one, they have to be probabilities in order for it to be a well-formed distribution without doing renormalization later. And you don't want to do that for computational reasons. Yeah. Good questions. Yes.
So when you say it almost always works, that means that it's more linear interpolation.
Regardless of the type of ensembling you do, I think linear interpolation is more common than log linear interpolation. But regardless of the type of ensembling you do, almost never had a situation where ensembling hasn't helped me, despite how I did it. You know, like despite the details anywhere. So just take the average. You know, make this equal to 1, or you know, 1 divided by n, or something like that. I think 1 divided by m would be better in this case than 1 would, because if you did 1, that would change the scale dramatically. But yeah, it's something that almost always works regardless of how you do it. Yeah.
Does it ever help to like fine tune the ensemble together by kind of running it on the train set and try to adjust the weights that way?
I'm going to talk about that a little bit later, but fine-tuning the ensemble might not be the greatest idea, and the reason why is because I feel that would correlate the errors. It would cause the errors to become more correlated, and it might actually hurt your generalization accuracy. So, that's a good question, though. I think potentially if you did it right, you could get it to work, but intuitively, you can think of a reason why that would not be a good idea. Yeah. Good. Okay. So I will move on to the next one. So one of the problems with ensembles is that they are very they're slow at test time, and they require training multiple models independently, which means they're slow at training time. So actually, maybe I'll do this one first, and then go back to the other one. So one way to help fix the test time slowness of ensembles is called distillation. And the knowledge distillation, basically what it does is it trains a model to copy the ensemble. Sorry, description should be distribution. Yeah, actually, sorry, this is very vague, so I'll try to write on the whiteboard a little bit more. So specifically, there's two types of distillation that are widely used in NLP. The first one is like prediction-wise. I don't know if this is the actual term they use in the paper, but like prediction-wise knowledge distillation, and another one is sequence-wise knowledge distillation. And prediction-wise knowledge distillation, basically what this is you take a big, strong model. Maybe it's an ensemble, like we're talking about here. Maybe it's just a huge model that you can't deploy on like a mobile phone or something like that. So you want to train a smaller model that does well. And what you do is instead of training the model to try to get the labels right, per se, on a labeled data set, you just try to train the model to match the labels that the larger model predicts. So if you have a probability distribution, normally what we do is we try to minimize the accuracy of the model with respect to the true label, where the true label is expressed as a one-hot vector like this. But what we do in distillation instead is we try to instead minimize the cross entropy with respect to the predicted values, like this. And just assume we have more predicted values here. And the idea is that the predicted values are kind of softer than the actual one-hot values, and they're more reflective of the confusion that a really strong model would have over the outputs. So there's two advantages of this. One thing is, for example, let's say you have noisily labeled data, or just legitimately very hard examples in your training set. So like, let's say you have a sheep that looks like a dog, or something like that in your training set. Presumably, even you're really strong for image classification or something like that, or since this is NLP, let's say we have a sentence where legitimately the sentiment is just not at all obvious from the sentence. So your really strong model would still be uncertain about that, so you wouldn't be trying to force your weaker model to learn and like fit that legitimately confusing example. Another reason why this is useful is you can actually do this on unlabeled data, right? So if you're just training a model, smaller model, to match the distribution predicted by a larger model, then the distribution predicted by the larger model, you can predict that on data sets where you don't even have labels. So this has been shown to be an effective way to train smaller models, more effective even than just training the smaller models directly on the labels. So mathematically, if we write this, what this looks like is P teacher. We call the larger model a teacher model. And P student, we call the smaller model a student model. And we minimize the cross entropy between these two distributions like this. The problem with this is if you have a sequence of, if you have a large sequence where y is, a sentence in natural language, there's no way to enumerate over all of the sentences, right? So because you can't enumerate over all of the sentences, one very common thing to do is instead just sample outputs, either by taking the maximum probability output or sampling outputs, and training the student model to, sample the outputs from the teacher model, and then try to train the student model to match the distribution of these sampled outputs. So this is sequence level knowledge distillation. I highly recommend this, this paper here because it very clearly lays out the steps that they take to go from the original, the math in this paper is very clear, so it's very easy to follow, and you'll understand well if you read this. Are there any questions about this before I step back to parameter averaging? No, okay. So, so this is one thing that you can do. Another thing that you can do is maybe not super intuitive at first, but it is kind of intuitive after you think about it for a little bit, which is ensembling means you have to do M models at test time, and at training time you need to train M models. So this is a method where you don't even need to train M models at training time. So what you do is you basically take you take your training run, and after each epoch, or like say after processing 100,000 data points, each time you output a model checkpoint. So basically you output your model after 100,000 training steps, then after 110,000 training steps, 120,000, 130,000, 140,000, maybe every time you evaluate on your development set or something like that. And when you do this, each of those models is going to be different, right? But they're all from the same training run, so they're very similar in a way. Like maybe each of the hidden nodes in your LSTM will still mean the same thing. They won't be like randomly shuffled where like node number 21 means the length of the sentence in one model and node number 51 means the length of the sentence in another model. So because these models are different but very similar, what you can do is you can just average their parameters together and use the model with average parameters from, say, the last 5 checkpoints in training, and use this to make your predictions. This is very easy to do because very often you'll be writing out checkpoints anyway, like when you evaluate on the dev set, so you can do early stopping or something like this. So just averaging them is a minimal amount of effort, no additional training time, no additional test time. This is something I can recommend. I've used it frequently in the past myself, so so this is a good technique to know about. Are there any questions here? Okay. Stacking. This is something that you can also do. It's basically you take one model and you make predictions with that one model, and then you take the predictions from one model and feed them into a next model. Yeah, it's something good to know about, but I'll skip over that. Okay, so the next question. Once we're yeah, sorry, go ahead.
This is a small question.
Yeah.
You said that the intuition behind like why ensembling works is that the errors are not so much correlated.
Right.
In the parameter averaging case,
Yeah.
parameters are kind of correlated. Are they the interval space
So yeah, that's a good question. So like I mentioned that decorrelation of errors is important. Um, in this case, yes, the errors that the system makes are going to be correlated much more than in other cases. But still, after each checkpoint, the examples that the model has just seen and are in the model's most recent memory are going to be different, right? Because even if you're doing it every epoch, you should be shuffling your mini batches every epoch, so the last things you see are going to be different. So there is some level of decorrelation of errors, just because the models are different in that respect. Yeah, good questions. Okay. Okay, so another important thing, how do we evaluate our systems? So the basic evaluation paradigm for any sort of text generation is usually we have a parallel test set where we have inputs and we have outputs that were annotated by human annotators. And use the system to generate outputs. Sorry, I wrote translations because I'm reusing this slide from something else, but we use the system to generate outputs, and we compare the outputs with this reference that we have. And these don't necessarily need to be translations. They could be summaries, they could be image captions, they could be dialogue responses, etc. So the perhaps the best way to do this evaluation is through humans annotating the results. And so basically, the humans will look at the results and say, given this particular input, people here probably can't necessarily read the input, but given this particular input, this output is correct. This is a perfect, I will, trust me, this is a perfect translation on the left. So, however, if this is the perfect translation here, what about this translation? This translation is not perfect with respect to grammar, but you can get the meaning perfectly fine. So we say this is an adequate translation because it conveys the meaning, or the meaning is correct, but the output is not fluent. Whereas this, flips the subject and object. So obviously that's a bad output. If you're evaluating other tasks, maybe your priorities are different. So this is just an example of the kind of priorities that you can have in translation, for example, but you could have other priorities like to give a very different example, like let's say we're doing dialogue and you're trying to ensure that somebody can buy plane tickets using your automated phone call system or something like that. If that's the case, whether you sold a plane ticket or not is an obvious evaluation metric you could use. That, I guess you don't even need human annotation. Another thing maybe would be how angry was the person at your system? How much negative emotion could you detect in their voice or something like that? So that might be something you would need to ask a human about. On the other hand, another thing I should mention is I'm talking about human evaluation. You can also do extrinsic evaluation on some sort of downstream task. So like, let's say you are doing, let's say you're translating a text and then running a QA system over the translated text to return a QA result. So you could also use a QA accuracy. I don't think this is in my slides, but this is another thing you could do, some sort of automatic extrinsic evaluation. Evaluation of the output, you can also do this by somehow taking the outputs and automatically comparing them to some sort of reference. So you take the system output and you compare it to the human-generated reference or references, and you say how closely do these match with respect to the words that you have in the output. So this is pretty good and easy to use, especially if you have really bad systems. But unfortunately, there's lots of results nowadays that show that our systems have gotten so good in a way that sometimes these sorts of automatic evaluation metrics are not correlating well with human evaluation. Another thing is for tasks like dialogue, there's inherently, dialogue response generation, there's inherently a huge number of outputs that you could make, or that you could have for a particular input. So this just does not correlate very well with human judgments there. There's a bunch of other metrics. I put Meteor up here as one example. Meteor is like the blue score that I talked about before, but it also has a bunch of extra tricks included in it, like considering paraphrases, or considering the word ordering in a more intelligent way than blue score does, or things like this. And there's a whole host of metrics that people have designed for things like this. I also don't have them in my slides, but there's also, we can also use neural networks themselves to evaluate our outputs. And there's one example of this is this paper, BERT score, evaluating text generation with BERT. So this is a paper that kind of had to happen at some point. Somebody had to evaluate text with BERT, and this is a paper that did this. But basically what they do is they take some sort of neural network model, they generate representations from this. And you either take the similarity between the representations and the representations of the human output, and say the similarity between these two is a good metric, or you could actually train a model to evaluate outputs. This also has its own advantages and disadvantages. One big advantage of using models like this is they're powerful. So obviously, they may give you better results than other ones. The big disadvantage is that when you're doing evaluation, it's very, very important for you to kind of trust it and kind of like understand what's going on under the hood and why you got an evaluation score. And if you're outsourcing that to neural networks, then you might get something that's better correlated with human judgment, but if you can't analyze it and understand it, how do you move on to like improving your model, for example? So, it's kind of like the general problem with neural networks in general. They're harder to analyze, but they're powerful. But I think it's particularly salient in the case of evaluation, because you really want to trust that your evaluation score is meaningful. So yeah, there's that. Okay. One final thing that I don't want to discount is perplexity. And I think perplexity, basically this is evaluating the accuracy of the probability distribution with respect to the outputs. I think this is actually pretty good, as long as you combine it with some other metric. I think it's a pretty good idea to do this because it's basically saying how well is your model modeling the probability of the actual outputs that you see. And it doesn't have problems like where, let's say the human reference randomly just used a different expression than the actual reference that you would have expected. So like say the dog barked at the cat, the puppy howled at the tabby, or something like that. The words are completely different, but semantically they're essentially the same. Perplexity, you would have to be able to assign some sort of probability to both of them to get a good perplexity. So basically, it is telling you, it solves this problem of coincidentally not getting the same output as you get a reference. I'll get to this in a second. One downside to this, though, is like, let's say you have a bug in your output generation algorithm, and your output generation algorithm is just generating garbage because you have a bug in your code. You will not catch that with perplexity. So like, I think it's obvious that you do need to have some sort of metric demonstrating that your outputs are reasonable, but within that, perplexity actually might be a reasonably good metric to measure quality of a probabilistic model over text. Yeah.
Can perplexity be used to compare inter one? Like, because in case there is one model and like the probability distribution that it is outputting might not be similar to the one that the other one is. So would it be a good idea to compare two different models just based on the perplexity score?
Could you compare two different models based on the perplexity score?
End of the day, that is what we mean by metric. Say I have a few scores and someone has X on few and I can probably answer. I just don't understand that kind of definition.
No, you can, so like I guess what I'm saying is Perplexity is a pretty reasonable way to measure whether Model A is better than Model B. A lot of people discount it for sequence generation tasks because it's not directly tied to the outputs you generate. But I think as long as it's combined together with something like BLUE or something like Meteor, then it actually is a pretty good way of measuring the difference between Model A and Model B, or the relative quality. Yeah. Any other? Okay. So with respect to, so I talked about evaluating condition generation. So how do we evaluate unconditioned generation models? So like how do we evaluate a language model that has no sort of conditioning whatsoever? It's not super clear. Like one thing we could do is human evaluation, but a model memorizes a corpus will be too good at this. So for example, I could give you a really good language model for generating books. This sounds really hard, right? I'll give you a really good language model for generating books, which is to walk over to the Hunt library and borrow a book from the library, and you have generated, you now have text from a good book, right? Presumably, if it's in the CMU library, it's probably a good book. So, hey, I've given you a model for generating books, but that is not going to be very useful for a lot of the things we want language modeling used for, right? Perhaps held out Perplexity is the best we can do at evaluating unconditioned generation models. Or perhaps we should use some sort of condition generation. So for example, adding a prefix to a sentence and then generating from that prefix is still condition generation, right? You're taking the prefix and you're calculating the continuation of a sentence based on that, based on what the model thinks is good there. And that's condition generation. You could say, is the generated output coherent with the prefix that you were provided with? And then that, at least you can evaluate. But I think maybe there's no better way to evaluate these model, like an unconditioned model than held out Perplexity. So, yeah. So are there any questions here? Okay, so I only have 5 minutes left. I'm going to go really quickly through just a bunch of different examples of conditioned language modeling. If any of these sound interesting to you, you can look up the references in the text, or in the reference section of the site. So if you talk about generation from structured data, basically one example of this is in a dialogue system where you have in the background it wants to provide some sort of information to you, like it wants to provide you information from a database, but you want to generate, okay, I want to find all of the examples of restaurants that are within a certain price range and kids are allowed and it has internet, and you want to provide this answer to the user. So you take in this structured data and you output it. Some other examples of this are generating summaries of basketball games from just the box score of the basketball game, generating Wikipedia articles from information about the entity included in the Wikipedia article. So there's lots of examples of this. This is an example from the box score thing. So for example, this is the box score, this is the article, the actual natural article. This is what a regular sequence model does, and it basically invents a whole bunch of facts about the game that aren't actually included in the original database. So recently people have been focusing on focused evaluation for this, where you try to re-extract the information from the generated article and make sure it matches with the original output. So there's some talk about this in the reference paper. Another thing you can do is generate from input and labels. So for example, if you have an input and you have labels and you want to generate an output, so this is an example where you take an input and some labels about what kind of conjugation you want for the word, and you generate the conjugation of conjugated word as the output. This is called morphological reinflection. Other examples are taking in a sentence and wanting to output a sentence that's more polite than the original sentence. Yeah, another example, which I think is rather poorly defined, is generating, taking a sentence and outputting it like somebody from a different demographic group said it. So like, what would this sentence sound like if, a person from Pittsburgh said it, or something like that. And then you would just add yens everywhere and fool everybody, right? Okay. Another thing is from speaker document traits. So this is a kind of interesting example of taking a TED Talk description and generating the TED Talk along with the biography of the speaker. Also from lists of things that you want to talk about. So taking in the name of a recipe and the ingredients in the recipe and generating a recipe. So you say, I want to generate pico de gallo, and it has chopped onions, onion, jalapenos, salt, and lime. And this paper has an example of a kind of creative way of making sure that you cover all the things that you're supposed to talk about, using something called a neural checklist model. And of course, this is super popular right now, generating captions of images or videos. So you take in an image and you want to generate the output. And this is included, you can use standard image or video encoders that are often pre-trained on large databases such as ImageNet. There's also things like visual storytelling where you have a sequence of pictures or video caption generation where you take in a video as well. Another thing is generating definitions of words from word embeddings. So you take in a word embedding and you want to generate the dictionary definition. So if you take a baseline being a standard sequence model and add additional information about like affixes and hypernyms, you can do a better job of this. So I don't want to spend a lot of time on any individual one of these because probably only 10% of the class is interested in any particular one, but this demonstrates how you take a conditioned language generation problem, come up with a creative model, and consult it in a nice way. So yeah, that's all I have, and we're a little bit over time, but I'm happy to take questions after class. So, thanks.